So this video is about observability for linear time invariant system. Let's first talk about the definition before I talk about example and the conditions. A linear time invariant system, which is typically given by this form, x dot is equal to ax plus bu, y is given by cx plus du, is said to be observable if for any unknown initial state. Okay, so it's unknown initial states, and there exists a finite t1 which is positive, such that the knowledge of this ut and yt over the time interval 0 to t1 is sufficient to uniquely determine my unknown initial state. Then it's called observable. If not, the linear time system is not observable. So from the definition we can say observability is talking about if we can use a series of the input and output to determine the initial value of the state. So here in this lecture, when I mention u, x, and y, what I mean by ut, xt, and yt, for abbreviation I use uxy. Okay. So before talking about the formal method or the conditions that guarantee the observability of a linear time invariant system, I want to go over a few examples to get a feeling about what we mean by observability. Okay, so let's just use a definition to see if you can verify the following linear system are observable or not. So first example says, if I give you a linear time invariant system which is x1 dot t equal to ut, x2 dot t is 2ut, so this is twice of that, and my y of t is x1t, x2t. Is this system observable? The answer to this question apparently is yes. The reason is I want to use some use of t and y of t, right? So given some input and some output, I can use that to figure out what is my state, initial state. Now naturally what I can do, I can say, oh, my yt ut is 0. If I set this to be 0, and if I do this one, this will be 0, all 0, okay? This will be always 0. So integrate this one, you get x1t. So integrate on both sides is x1 dot t 0 to t, for example, dt is integration 0 to t. If I let this to be 0, 0 times dt, right, over dt. So this says x1t, so integration on left side is x1t minus x1, 0, and right hand side is just 0, which means yes, my x1t is just equal to x1, 0. So my solution is a constant. Apparently yes, because the derivative is 0, so this x1t is a constant. The constant will be equal to the initial value. Yeah, as long as I make u1t to be constant, to be 0, now my yt, the first output will just tell me what is my initial value. Of course, you do the same for the second one, x2t. If you let ut to be 0, and my x2t is also equal to x2, 0. So which means my second output will also determine my initial value of x2t. That's why it's observable. Okay, let's go to the second example. What if x1t is equal to ut, x2t dot t is 2ut, that's the same thing, okay? And my yt is x1t, okay? The difference is I don't have x2t anymore. Is this observable? Apparently this is no. Okay, the reason because my x1t, my yt only relate to x1t, and x1t, x2 they are decoupled, which means that whatever x1t is changing, is evolving, does not depend on x2t, which means my output is only related to x1, has nothing to do with x2. That's why it's not observable. Okay. The third question says, hey, I still keep the x1 dot t and x2 dot t to be the same, while my output becomes x1t plus x2t. So is this observable? So it's a little bit hard to figure over here because I do have x1t and x2 in my output, but it's a sum of those, right? So what's going to happen? Okay, so that's why it's important to take a look at what are the conditions that can guarantee the observability of a linear time invariant system. Okay, it's not easy to just use a definition. It's important to figure out what conditions we can verify if a linear system is observable or not. Okay, next what we're going to talk about is the conditions that can guarantee the observability of a general linear time invariant system. Okay, to analyze that, we want to simplify the problem a little bit. Okay, here's what we're going to do. So if you look at the solution of the linear time invariant system, okay, this is the solution to xt, right? And this is solution to yt. Okay, this is the standard solution for linear time invariant system. I don't want to repeat over here. So if you look at this one, now the output for my yt has two components. One is this. So this part is related to x0. This is what you want to figure out, right? This is what we want to know. Okay, but this side, this part is nothing, is not related to my initial state. Okay, what does it mean? Okay, if I move this one to the left hand side, right hand side only keeps this. Okay, so I have yt minus a whole bunch of stuff, and right hand side only keeps this. Okay, if I would define this left hand side, which is yt minus a whole bunch of stuff, as y tilde t, is a new yt, y tilde t. Now I can write this one. The y tilde t is, so this is xt, and y tilde t, sort of xt is just EAT times x0, and y tilde is CEAT x0. So you sort of say, you sort of make sure this is sort of 0. You almost make this one to be 0, right? You make this, if you make this 0 to be 0, right, this is all gone. This will be gone. The solution xt will be this, solution yt will be just this, right? So apparently, as we can see from here, it doesn't matter, it really doesn't matter what you select, because I only care about this one. You want to use yt and ut to figure out xt. It only matters the arrow, right, to determine my x0, right? So it doesn't really matter what ut you use. So it turns out the observability of this linear time invariance, this general form, is the same as the observability of this guy. You sort of consider this as y tilde t over here, okay? You sort of consider your ut is always 0. You can say my ut is 0, okay? All right, what we have makes this simplification of observation is the observability of a linear time invariant system of this general form is equivalent of the observability of a linear time invariant system given this simplified form. That's because my yt and ut is only matters the differences. It doesn't matter what the absolute value of u is, what the yt is. So we can select ut to be 0 and make it more convenient. So here we come to the conditions that can guarantee the observability of linear time invariant system. So this is a condition that can guarantee the observability of a linear time invariant system. So this a theorem says a linear time invariant system given by this form, which is also, it also applies to this guy, okay, is observable if and only if any one of the following three conditions holds. Okay. The first condition says the WC matrix. Okay. The WC matrix is right over here. WC matrix is integration from 0 to t E A transpose times tau times C transpose times C times E A tau d tau. So this is a matrix, this is a matrix, this is a matrix, this is a matrix. So it has nothing to do with B only and D, only related to A and C. If this is a matrix, integration of this matrix product from 0 to t is invertible for any time t, which means WC inverse exists. Or we can say the determinant of WC is not equal to 0 for any t. That's equivalent. Then this is the original linear time invariant system is observable. This is the first condition. The second condition says this O It's also called observation matrix, observability matrix, which is given by C times A. So your first row is given by C times A, the second row is given by C times A squared, so on and so forth until you do C times n minus 1. Okay, so the n is the dimension of x, which is how many states you have. If this guy has 4-column rank, which means the rank of C is also equal to the dimension of x, it is observable. The last condition says the rank of C, you put a C right here, and you put an A minus lambda I below that. This is a matrix. The rank of this matrix is n for any eigenvalue of A. If this holds true for any eigenvalue of A, this rank is equal to n, so this is controllable, observable. So there are 3 conditions. So the most popular one is this guy. The second one is the most popular one, and first one is also useful. Okay, and last one probably they're sort of equivalent, but first one probably a little bit more popular than the last one. So the second approach was the most popular one. Okay, now let's go take a look at the example I mentioned before, the one I left. I haven't talked about. In this example, I haven't talked about observability. Now let's go to revisit this example again to see if it is observable using the approach I mentioned below, the 3 conditions. So the problem I have is x1.t, okay, is ut, x2.t is 2ut, and yt is x1t plus x2t. So I drop the t notation here. So if I do, because I have to write this in this form, okay, to figure out what my A and B and C and D, in particular A and C, B and D, they don't matter, okay. So if I define my state as x1 and x2, so I can write down this one and this one as x dot is equal to 0, 0, 0, 0 times x plus and 1, 2 times u, because this is you do so 1 or 2 times u, okay. Here I can say that n is 2. Because we only have 2 states, so the number of states is just 2. So n is 2. Okay, I want to make sure that the rank of my observation matrix is 2. So we use the second approach, the condition, to verify if the linear time invariant system is observable or not. So let's compute that. So observability matrix is given by here C and C times A. Okay, if you look at this one, so this is my A, B, and C. So it really doesn't matter what B is. So my C is 1, 1. So it's 1, 1. And the second one is C times A, right? C times A, C is 1, 1. My A is 0, 0, 0, 0. So this gives me just 0, 0. So I put a 0, 0 over here. So apparently the rank of this guy is 1, right? The rank is 1. So these 2 columns, they're the same. So the rank is 1. The observability is 1, so which is less than 2. That's why it's not observable. So the reason we can interpret this, if you use the definition to interpret this, the reason this is not observable because I can only observe x1 plus x2. Okay, remember from the previous discussion. So it doesn't matter what u you give. So I can say u is 0. Like get it. Of course, here I mean u0 is ut is always 0, right? So when you do this way, the solution for x1t is just x1, 0. Solution for x2t will be x2t is 0. Oh no, this is x2, sorry. So my y is just y, t is just x1, 0 plus x2, 0. The reason it's not observable because I can only observe the sum of the 2. Okay, I don't know. I know the sum is 2. I don't know, but I cannot figure out what is x1, 0 and x2, 0 individually. Because if the sum of 2, let's say if the sum is 3, for example, you have many options. Even if I tell the initial condition for this is 1 and this is 2, yeah, you can observe the sum is 3, but you cannot use the y to figure out what is the exact value of x1, 0 and what is the exact value of x2, 0. Because we don't only know the sum. That's why this is not observable. Okay. So let's go to the next example. So here the second example says x dot t is 1002 xt plus 11 ut, and yt is 11 times xt. Okay, let's see if this is observable or not. Okay, if we use still the same approach to compute the observability matrix, so this is given by C, and C is C and C times A. The reason I don't have more because this is given by C, CA until CA n minus 1. Okay, so n again, this n is 2 because x has 2 states, so n is 2. So I only do C, CA until C n minus 1 is until CA. So I only have 2 terms or 2 rows. Okay, so C is 1 times 1, 1 1. So I put it over here. C times A is 1 1 times A is here, 1002, which gives us a 1 or 2. So I put a 1 or 2 over here. Apparently this row and this row, they are independent, so the rank of O is 2. Okay, because the number of linear independent rows are 2 because they're independent. So rank is a 2, and n is also 2, which is equal to n. So this is observable. Okay. The next example says x dot t is 1001 times x plus 11 times u, and y is 11 times x. Again, here x is xt, u is ut, and y is yt. So we can still use the same approach I mentioned before. The second approach is to compute the observability matrix O, which is again is C and CA, because n again here is 2. Okay, so C is still 101, put over here, and C times A is 1 times 1 times A. A over here is 1001, and the product of these two will be just 1 1. So we put a 1 1 over here. Apparently these two columns, this column, they are the same, so they're not independent. So the rank of O is equal to 1, which is less than 2, which is number of n. So this is not observable. Okay, to summarize, we talk about here is for the linear time. So this is the summary. So for linear time inverse system, x dot is ax plus bu, y is cx plus du. Okay, it's the observability of this guy. Observability of this guy is the same as observability of x dot is ax, y is cx. Okay, and the condition, the most popular way we check the observability of this linear time invariant system is given by O, which is CA, CA until CA n minus 1. So n is the dimension of x. Okay, we check if the rank of this matrix O is equal to n. Yes, observable. No, unobservable.